Everybody, this is Avantik here. Today we'll be discussing about dealing with imbalanced classes. The agenda for today's discussion would be understanding what are imbalanced classes, their impact, oversampling, undersampling, connecting sampler to pipelines, making classification aware that the data is imbalanced and it can do something internally about it, using anomaly detection for dealing with imbalanced classes. Let's first understand what are imbalanced classes and their impact. Imbalanced classes and their impact. Data with skewed class distribution are known as imbalanced classes. Examples of those are spam versus ham mail. Generally, 95% of your mail will be spam, right? So if you want to create a spam predictor, it will be getting an imbalanced data with 95% of it as spam. If you have tumor data, then predicting if the patient is suffering from cancer or not, right? Very much imbalanced data. So what happens is the classification algorithms are more prone to predict new data's class as the over representative class, right? So that's the whole point. And as far as matrices are concerned, accuracy score is not the right parameter to be used in case of imbalanced classes. That's because it will anyway tell you correct class classification divided by total class classification. So if you have 95% data belonging to one class and it predicts all of them as 100% data of that higher bigger class, it will anyway have 95% accuracy. So that's not the right measure. You might have to use matrices like confusion matrix and recall precision techniques. Okay, let's now generate the data and see how this works. What we're trying to do here is we are trying to generate imbalanced class of data here. Okay, you are using make blobs, and this is how we are generating the data. Yellow data is class 1 and purple data is class 2. Okay, so we can see yellow is a smaller representative of data here. We want to see if the regular algorithm without any sampling technique, if they work well and what is their behavior based on this. So based on the above data, we have trained the model, and as always, we try to generate all the data so that we can see the decision boundary. Okay, and once we predict, we can see the separator is predicted as this, right? So you can see half of the smaller representative class data is getting misclassified. Okay, so that's the concern here. Okay, so to deal with such situation, the Imbalanced, this is the third-party library which provides a lot of sampling techniques implemented in it. Going forward, we'll try to learn all of them. The first, we'll understand oversampling. Oversampling. One way to fight this issue is to generate new samples in the classes that is underrepresented. Okay, so in the above example, we have A and B. So assume that A is the class which is underrepresented. That means there are lesser samples of it. You'll try to increase the number of samples in that class. The most simplest approach to do this is multiply them, right? So we can do that with random oversampler. It just repeats the undersampled contents. That's all. Okay, so we can see here it's generating three distribution. One is 1%, 5%, and 94%. So this is the data that we see here, right? So now if you use this data for our training our model and all, so this is the separator that you see here, right? This is the separator. Okay, using SVC, this is the separator, this is the decision boundary that is predicted. Now we want to use the sampling technique, random oversampler, and see what is the impact. Okay, so we can see here, this is the instance of the random oversampler. We are training it with our data, and it is generating X resample and Y resample, which is like generated data. Okay, so here the classes are no more imbalanced. Okay, you can see this purple dots, which are smaller, will become dark because it generated data in those areas. Now we'll use this in training our model, right? Fit X resample, Y resampled. Okay, on doing so, you can see the decision bound, and this is similar stuff as we do earlier, like generating the data for all the area, and we try to predict the decision boundary. As you can see, decision boundary is shifted now. Okay, so because of your sampling of data, you get a more better, you get a possibility of a better decision boundary. Okay, and post that, if you want to print the confusion matrix, which will show the misclassification and all that information, you can see it over here. You can refer to the matrices module for understanding more on confusion matrix, but as far as it is concerned, the diagonal represents correct classification, and the values below the diagonal, above the diagonal, represents misclassification. Next technique for oversampling is smooth synthetic minority oversampling technique. That's smooth. Okay, so what we do in this technique is you try to interpolate the data from the existing data. You anyway have to increase the samples of underrepresentative class. You will try to generate some data from it. It will not be duplicate data, it will be generated data. So that's how you create import smooth. This is a creating an instance fitting the sample, and you're plotting it. You can see this was the data earlier, it is generating more data around it, more data around it, more data around yellow. So okay, so these were the under sampled classes, so you can see the representation, I mean more data generated for all these. Now if I use this sample data to train the model, you can see a different decision boundary compared to uh, without sampling model, right? So again, we can plot our confusion matrix, which will show the distribution. As you can see, this is different from your random order sampling, right? You can see here it's a little different from that. Then you have another technique, adaptive synthetic sampling method. Okay, this is similar to smooth. It will generate the data, but the thing is, it will generate data corresponding to the original data which were misclassified. Okay, so smooth does not consider this situation of getting misclassified and all that. It will simply generate data. This guy will see it is not generating data for this area. It is generating data only for this area because these were highly misclassified. Okay, so that the chances of getting them classified correctly improves. Okay, so of course in this situation we don't see a lot of improvement. Okay, but a very different decision boundary in this case, right? So it impacts. If you do sampling, it has impact on the data. So depending on which sampling is working out for your particular data, you will choose that. Okay, of course that is the subject of experiments. And like earlier cases, here also we'll try to plot the confusion matrix, which will give us clarity what is happening where. Okay, and followed by this we'll understand undersampling. This is basically try to deal with the data which is over representative, to bring it in the same scale as the underrepresentative. Undersampling, reducing the data of the overrepresented class. That's the whole philosophy around it. So for the first technique is random undersampler. It randomly picks up the points from the entire data set of overrepresented class, so that it is in the same scale as the underrepresented class. Say we have data like this, okay, and we are using random undersampler, and it will generate X resampled and Y resampled. Okay, so on plotting this, we can see rather than a dense yellow thing, we have a lighter yellow version, and we can see all these classes are equally balanced now. The number of samples for all these classes are equal. So this is your uh, this is your undersampling technique, where you try to minimize over represented class. And we can see using this counter method. So before undersampling, this was the distribution. After undersampling, this is the distribution. The next method is cluster centroid. Okay, it has its roots in k-means. Rather than choosing data from the existing data set, what we try to do is we try to find the representative data. For example, we have this over representative classes. What we want to do is we want to get like in this case, the amount of number of points in underrepresentative classes 64. So we want 64 representative data from the oversampled classes. We can use k-means here with 64 clusters, and the center of each cluster is now representative data. So we don't use actual data, we use the representative data. So all these yellow points here, it's the representative centroids of 64 clusters created out of the oversampled data, right? So cluster centroid is another technique by which you can do undersampling. After this, there are, you can refer to this Imbalanced library for, right, Imbalanced. You import this using Learn, okay, under sampling. You can refer to this library for more sampling techniques. But once you have chosen the techniques, or want to choose the technique right, you have to make it part of a pipeline so that you can validate and do other things around it. Let's see them. Connecting sampler to the pipeline. This is what happens most of the time. If you want to find which sampling technique is working well with the rest of the estimator and pre-processing techniques, you have to put it as a pipeline and validate it. Okay, but remember one thing, that regular pipeline does not work with sampling techniques. So you have to make use of make pipeline, which is present inside IMB learn pipeline. So here, using make pipeline, you are giving this first sample over sampler and the under sampler, right? This is the SVC kernel over here. These are two pipelines. You're putting these pipelines in the list and training them together. And then for each of the pipeline, you are plotting confusion matrix. As you can see here, you, okay. So based on the confusion matrix, you can take a call which is working out for you. Okay. The next technique thing that we'll discuss is, rather than dealing with the data, which sometimes is possible and sometimes does not work, you might want to tell the algorithm that they have to deal imbalance of the classes internally by using penalty mechanism, where if the data is getting misclassified and data belongs to a smaller class and getting misclassified to higher class, will give more penalty, right? You can use all these techniques. So how this thing works is, like for example, all the algorithm like logistic regression, SVC, naive Bayes, right? All of these algorithms have a way to assign weights of distribution of data, right? For example, if this is the simple data, you can see here, this is the distribution, and you can configure class weight in SVC here. When you do so, what algorithm does it derives the distribution information from the data itself. Once it does it, okay, so it has a higher possibility of giving better results. As you can see here, this results is little better than this, because the model is aware the data is imbalanced here. The next technique that we can use to identify imbalance situations is anomaly detection. Anomaly detection, another way by which we can find out the right class of undersampled information. Like, let's see how it is done. Okay, so we are generating data and we have two classes over here, right? If we use anomaly detection technique like elliptical envelope, it tries to find the bigger envelope here, right? We are giving a contamination factor 0.1 so that only 10% of the data is detected to be outliers. And you can see here, it detected these data. Some of more data are there, but as outliers. Okay, so we can say that outlier are actually data belonging to a smaller class. So this is one technique with proper configuration and finding out which is the best anomaly detection, which is really predicting the class itself, would work out for you. Okay, that's all from this video. Thank you.